Okay, so to start here, so I'm going to tell about Neuronflow. I have been working on this for years. I'm a bit tired of talking about it. That's why there was no abstract for the whole time that the program was there, because I was thinking, what can I talk about which is not Neuronflow? But then I realized, yeah, at least this time it's going to be this. I promise next time I'll try to talk about something else. So what we are doing with Neuronflow is a computer architecture for an NPU, which is supposed, well, it is actually. I'm still trying to believe myself that it's as low power as it really is, low latency, and we are designing it for augmented reality, so see-through AR. I'll tell a bit about it. So most of the work is done. Of course, we work for Snap. We were originally a startup. We were trying to do a lot of different applications. But since we are at Snap, the focus is on designing a processor for spectacles. Actually, we changed names. Now we call them specs. The idea of specs is that you have augmented reality glasses. A group of people that is using the same augmented reality glasses is going to actually see the same overlays. So you can, for instance, have, I don't know, I guess this is supposed to be a game of Dungeons and Dragons, and everybody can see the same layout of the game, because the glasses do the job of showing you the same 3D environment. This is the old version of the glasses. Last Tuesday, our CEO presented the new ones that start looking a lot more like something that actually you would not be embarrassed of using. I actually think the new model does look pretty cool. The only thing is that you do notice that this is a bit heavy here on the sides, because that's where the batteries go and some of the logic. The processors are placed on the sides, also in the middle. There are cameras, 4 cameras on the device. And there's a ton of different AR applications that you can do with it. These are just some examples. Like you can have a board game. You can have magical creatures that are walking around with you wherever you go. You can actually have your own personal Pokemon that walks around with you everywhere you go. You can do paint shop in the air, which is actually fantastically, surprisingly fun. Like you draw something and you can actually walk around the thing that you drew and see it from a 3-dimensional perspective and share it with other people. Of course, you have lots of games you can do with it, and we're also looking at a lot of tutorial-like applications, and also some applications that actually teach you how to do a certain task, like teaching you how to play basketball, for instance. Although, given that we just announced that they are going to cost $2,000 this model, you can order it, but it does cost $2,000, actually a bit more than $2,000. I don't know if you wanted to take it to the basketball field with you. But if you go alone just to train the shots, I guess it will be okay. What's our job in this? Well, mostly the processor that we are designing is going to do AI computer vision tasks, actually. And the main task that we had to solve was, and it's probably the most important in the device because it's the main interface of the device, is it's hand tracking and hand detection and gesture detection, actually. So you detect where the hands are. You make a skeletonized version of the hands to have very high accuracy gesture recognition, and then you perform gesture recognition on those 3D models of the hand that you generated. It has to track 2 hands and always recognize one hand from the other. It has to be always on. It has to be very accurate, so within 10 millimeters. It has to work indoors and outdoors, which is a big problem because with very different lighting conditions, the network is going to behave differently. The latency has to be very low, below 5 milliseconds to do the full hand detection and tracking for 4 cameras at 60 FPS, which in fact means that we are running it at 240 FPS because we run the same algorithm for all the cameras. And oh, that's a one less zero here. I mean, this is nothing. This we could do 10 years ago. No, below 250 milliwatts. Sorry, typo. I apologize. It's 250 milliwatts, 2,500. I'll be fired tomorrow. Yeah, no, this is not. This is not. Anyway, just to tell you who my team is. This is the architecture team. I'm the worst player of all. I actually was the worst of all in this Laser Quest thing. We have several students working with us, so you can see the 3 on this side, except for me, are students. So, architecture of this thing. So the whole architecture, I'm tired of showing this slide, but the whole idea is that the architecture is exploiting sparsity. So we designed the architecture under the assumption and actually the observation that there's a lot of sparsity in the data that flows through a neural network. Even if you just use a ReLU activation function already, about 50% of your activations will be zeros. We can actually train and induce activation suppression, meaning that we can get this much higher, as I'll show afterwards. And you can also exploit another type of sparsity, which is if I compare 2 consecutive frames of a video, you're going to see that the difference between consecutive frames is very small. And actually, if you'd only process the change, you'd have a lot less to process than if you have to process the whole image. We also use another one, which is spatial sparsity or line sparsity, where we use some of the results of one line to the next line because very little changes from line to line. So this is just the idea. So if actually we can process only the non-zeros, we should actually be lower power and lower latency because we have a lot less load to process. But this has consequences for the architecture. Typically, you exploit a lot the regularity in the execution of a neural network. If I'm doing sparsity, I cannot exploit sparsity as easily. I want to skip activations, which means that I get much more irregular execution patterns. And worse, those execution patterns are dynamic. So actually, we actually have to execute in a different way. Most people will tell input stationary execution is less efficient. It is. However, under high sparsity conditions, it can actually operate better. We designed for event-driven or input stationary execution. Why? Because essentially input stationary execution makes it easier for us to skip at a coarse grain activations. So if an input is missing, I don't need to do all the multiplications related with that input. But it does have a problem, is that I have to store intermediate results more often. And intermediate results are more expensive to store than inputs because you have to do a read and a write instead of doing just a read. So we made a kind of analysis to see when sparsity would start gaining us in terms of power consumption. And actually the results were not very good. So essentially you see here the inverse of sparsity, which is density. And what we see is that the memory access ratio with sparsity, so of input or input-centric versus output-centric, only evens out at a very high level of sparsity, about 90% sparsity. However, that only takes into account exclusively the memory operations. If instead of that we take into account several parameters of the architecture and all the other expenditure of power that you get in the execution, actually the break-even line becomes somewhere around 70% or so, dependent on some assumptions. So if we manage to have more sparsity than that, the architecture is going to be effective in terms of power consumption. What this doesn't show is that in terms of performance, we always gain, because essentially whatever event density we have, we are actually reducing the amount of cycles that we have to execute, and that's going to speed up the device no matter what. So latency we gain directly. Power consumption we have to make up for what we are wasting in having more accesses to the memory. The chip, I removed that from the slide and there's something missing. Anyway, the current, I tried to update the slides and apparently I did it a bit too fast. So the current taped out device, so we are in the, actually we are already above, but the last one taped out is Neuronflow 4. That version of architecture was taped out at 5 nanometers, 144 SIMD cores. Actually, this is no longer right, it's 850 megahertz. Each core has 256 kilobytes of memory, and it's all in FP16 algebra, but everything can be quantized at 8 bits, 4 bits, and 2 bits. So for data storage and reads and writes, we are actually just paying for reads and writes at 8, 4, and 2. It's just the computation is always done at 16 because that gives us accuracy that actually distinguishes this device from other devices that were benchmarked by Snap in terms of the accuracy that they needed for the network. So the FP16 is really a need in terms of accuracy of the networks. It is an array, so you have all these cores. They are connected by a network on chip, and they communicate via events. That also reduces the communication in the network because we don't send all the data. We just send the data that matters, the one that is different from zero. What else to say about this slide? Yeah, I said this so many times that I'm starting getting a bit going on. So essentially each core implements a simple data path. What happens in that data path, we have several event FIFOs. Each one of them receives inputs from the previous layer. Those are decoded and then they're executed in parallel. So you have two types of SIMD. We have SIMD at the level of the number of output channels that we are executing at the time, and at the number of input channels that we are overlaid at the time executing. So we have essentially SIMD 4x4, 4 inputs for 4 outputs, all in the same address. Actually, no, I think it's more in the last, but this is version 4. What I wanted just to focus a bit here is that, so you heard in several of the presentations today about performance. When you're doing something on Edge AI, and especially if you have an architecture that is as unconventional as ours, you depend a lot on training to actually get better performance from the device. Yeah, and we do all of these. So we do weight pruning, we do weight quantization, we do activation suppression training, we actually do adaptation for temporal sparsity. We use neural architecture search, and actually we use a version of neural architecture search specifically to improve temporal sparsity. And I'll try very quickly to go through those. So weight pruning is mostly about lowering number of computations and memory accesses, because if we have fewer weights, we also skip those, and that saves us some computation. Weight quantization essentially does the same as pruning, just in a more at a different level, but essentially it's going to define how much input we have to process. Typically, you were asking the question of which one do you do first? Yes, we do both, dependent on the network. We actually have parameters to actually run quantization before or pruning before, depending on the graph that we are handling. Activation suppression, we actually train the network specifically to actually do fewer activations. This gives us a factor of about 2x in performance. Oh, sorry. Oh, I forgot. I thought it would work, but apparently it doesn't, so sorry. Temporal sparsity, essentially actually temporal sparsity we don't need to train for. If you just actually switch on temporal sparsity, what you do is that we remember the result of the previous computation and then we compare them. If the result is the same, we don't send. But it costs a lot of memory because you have to remember the test. I really have to speed up. It costs you a lot of state, and because of that, we develop a technique with neural architecture search to actually reduce the cost in terms of memory. Typically, it would cost 5x the memory that we use in a normal execution. With our technique, it costs only 20% extra. So very quickly going through those. So there's the technique that we use for activation suppression. You can see these are results on compute latency reduction and power reduction. You can see that induced sparsity for these particular networks on ImageNet, which is a very difficult data set for us because it's the most demanding we have. You can gain about 70%, 60% on both latency and power for several of these networks. EfficientNet is more difficult. If we add neural architecture search to it, so we do neural architecture search essentially because you see that for different architectures, the best network has a different topology. And in fact, because Neuronflow is a very non-stat architecture, the mobile networks are not designed for us. So we really have to adapt to what we do. And I have here an interesting result, which is we took EfficientNet and on the front-hand data set, which is a hand tracking data set. And what you can see is that if you take the original network and then we do a search for better networks for our platform with the same base as EfficientNet, you can see that the performance can improve by a very large factor. So the latency is reduced to 40%. The energy is reduced 50%. And this is essentially just a network that does exactly the same, with the same exact efficiency, quality. The problem, of course, is that it takes time to get these results. You have to run the neural architecture search for quite a while. And the other problem with neural architecture search is very dependent on your prediction model, on the quality of the results of your on the quality of the results on your hardware. You cannot have hardware in the loop, because that also means compiler in the loop, which means that you have to compile every single network you try, then run it on the hardware and bring the results back. So actually we use predictors, but designing good predictors is pretty, it's an area of research in itself. Yeah, you're laughing because you work on the predictors that we use, yes. So about temporal sparsity, the main idea that we did in temporal sparsity was using neural architecture search too. So the problem of neural sparsity is that all activations have to be stored and remembered in order for you to compare them to see whether you need to process again or not. What we did to actually avoid that was that we redesigned, we took, in this case, MobileNet v2, we redesigned MobileNet using NAS to have more weights and fewer activations. And like that, we get an equivalent network in terms of accuracy that is much more efficient when it comes to to the amount of states that it needs to hold to remember what did in the previous iteration. So you can see the results here on hardware. So this is from our 5 nanometer chip. And it's with the old version of the architecture. So with the new one that is fitting this model better, the results should be quite a bit better. But you can see that temporal sparsity gives us an acceleration over the baseline of almost 4 times. But it costs a lot of memory, so we need 11 megabytes of memory just to hold the state. In a version that uses our NAS, we actually reduce that by a large factor, the amount of memory on state that we have. But we also, in this case, we lose some of the acceleration. We go only for 3 times. In MobileNet v2, actually, we managed to match. So this is for temporal. Just one more thing. So I didn't mention any transformers, right? All the architectures I showed here were convolutional networks. We also run transformers. The thing is that Neuronflow 4 was not designed at all for transformers. It was designed only to run convolutional networks. So when we start picking transformers, we realized that just running a transformer directly would not work. First, we don't have enough memory for all the parameters of a transformer. Second, we didn't have some of the functions. We didn't have a support for JLU, for instance. So what we did was we took a transformer, we actually rectified it, that is meaning removing all of the stuff that we don't like and put ReLUs instead. And then we did a number of optimizations on it. So we used unstructured pruning, quantization, structure pruning, and we ran our activation suppression algorithm on it. So the result was that, so what does rectiformer mean? It means that we replaced several of the functions. Let me see, like the layer norms, we replace it by dynamic 10H, which our architecture supports. Softmax was actually just unceremoniously dropped and replaced by ReLU. Jelly was replaced by ReLU, and we just retrained. The interesting thing was that the first thing was that the network remained with the same accuracy that it had before. The memory reduced by a factor of, if I don't have it here in the slides, but at least 50%, I think more actually. And in terms of performance, if we take the sparse baseline, so the base rectiformer, and then we try to see if we induce sparsity like we did in the convolutional networks, we did it. And we even got an acceleration which is higher than what we normally get in a convolutional network. So it means that vision transformer is actually very amenable to induce sparsification. So to conclude, so event-driven execution can deliver very high performance by exploiting several forms of sparsity. The training and network design optimizations can really improve the sparsity exploitation very dramatically. Induce sparsity through training helps a lot. NAS for low latency and low power has helped a lot, factor of 2. Get another factor of 2 on temporal sparsity by redesigning the network for sparsity. And vision transformers are good for event processing, as good as CNNs. Sparsity is still there to be exploited. We can increase it by using accuracy neutral adaptations. And for larger models, we may need extra background memory. So we are looking at LLMs. LLMs, for instance, we cannot use these tricks. What happens at first, we cannot retrain the network. We can only fine-tune. And the other thing in an LLM is that the amount of memory is so large that you have to use things like a KV cache, and its architecture was not designed for it, so we have to redesign several parts of the architecture if we want to go there. But for vision transformers, which was what we mainly wanted to support, the architecture works. And I'm sorry, I'm very late. Yeah. Yeah.